Welcome back, everybody. Let's talk about mass spec of esters. So we have talked about mass spec of a lot of functional groups. So you are seeing trends, I'm sure, if you've been following them. But this is just a unique functional group, and there are lots of possibilities for esters because, as you can see, it's got two oxygens here. Let's see what are the possibilities for this molecule when it travels through that mass spec and gets hit by lightning and has its electrons just ripped off. Let's look at it. So here is a molecular ion going through the machine, and bam, wham, one of these electrons. I mean, there are lots of lone pairs here, but let's say something takes this one off, and you are going to get your molecular ion peak, which is going to be just the same weight as this. The electrons really are so tiny, you're not going to see the mass loss on the machine. So you're going to have a molecular ion peak here at 144. But then as you can see, it's not there for too long. I mean, it's just as soon as it's formed, it's breaking up into these fragments. So that's because there are lots of possibilities for this molecule, and it just tries to go to more and more stable things. So let's see what it is. So let's see, we have over here, well, there are possibilities. You can break it up here, alpha cleavage. You can also do, as a long chain, alpha, beta, gamma, the McLafferty rearrangement. So that's a possibility. And then, well, obviously, we got more than that. Let's talk about possibilities for this molecule going through the machine. Let's talk about, well, you can have, I'm just going to label that. Both of them are going to be like alpha cleavages because it's right here. So let's see, you have this molecule here, and you have a carbonyl, which is hungry for electrons. And you have, well, this is a molecule here that's electron withdrawing as well. So this is pulling electrons, that's pulling electrons. It's only a matter of time when this bond is severed, and you get a radical here and a cation here. So this is your A. Again, alpha cleavage here is going to give you a triple bond now. So only got one lone pair on it. Therefore, 1, 2, 3, 4, 5 is a +1 with a long wiggly tail. Plus, you are going to get this coming out. So the weight, molecular weight of this is going to be 99, and you can see that's quite a big peak here, 99. And here is a 45. So both of them combined would give you a 144. Let's do the same thing and try to chop it up on the other side and see what goes on. So here is, let's do the other alpha here. Let's do the B, alpha cleavage. Let's see what would happen if you did the exact same thing on the other side. So here is your alpha carbon here, and here are two electrons, and that can form a bond here and kick out that long tail, pretty much getting rid of its long tail here. So once it breaks up, you can see how you would get a fragment here. Now that's going to be your triple bonded oxygen, which means you got 1, 2, 3, 4, 5. 6 minus 5 is a +1. And the long tails kind of wiggle its way out of the machine through the vacuum. And you are going to see a recording here for this at 73. And this is going to be 71, both adding up to a 144. 73 is here, but we missed a very important peak, basically the base peak, 100%. Well, if it's 100% means it's occurring more frequently and the fragments lasting longer than the others. I mean, it's still very small, like a microsecond, 10 to the -6, or below. That's the time frame in which these molecules travel. I mean, they're going super, super fast. So 10 to the -6 seconds, maybe around that time. So, well, that's a long time in a mass spec. So let's see what is out there that's going to stay at 88 molecular weight. Let's look at another possibility. We did alpha. We didn't do beta yet, but we could do gamma. So this is alpha, beta, gamma. And on this side too, you have them. So let's do, let's say, C. So gamma cleavage is also called the McLafferty rearrangement. So write that down. I mean, I have done gamma cleavage a lot, but I don't always write it down. This time I am going to. So here, well, if I want this gamma over here, I would have to move it and write it out like this. So here's your alpha, beta, gamma, and the hydrogen is just at the right height for it to, this carbonyl to just pluck it out. So here is your carbonyl here, and that's your molecular ion peak. Well, it is going to fragment this entire molecule and give you a peak. So over here, you can see the hydrogen going away with this oxygen, while this breaks up and forms a double bond there. 2 electrons here. The other one forms a double bond here with the remaining electron from that CH bond. So you have a hydrogen moving over to the carbonyl, and you are going to then form a bond. So you broke that double bond and you are forming a single bond here to the hydrogen. This lone pair is here. You still have a positive over there, and this becomes a double bond. Now I didn't draw the hydrogens over here, but you can see how that could be like an enol radical cation. And this tail then goes away with an alkene. This is going to be 56, and this is going to be 88. So that's a most stable peak. So we kind of accounted for all of these now. And let's look at why that would be so stable. Well, if you look at it, there's a lot of possibilities for resonance. So resonance stabilized cation here is going to be the reason why this is going to be so stable. I can say resonance stabilized. So typically there is a reason why the base peak is the reason why that's 100% relative abundance. There is always some reason due to hyperconjugation or resonance or some extra stabilization like aromaticity and so on. Or it's a tertiary carbocation, all of those reasons. And sometimes things even rearrange to get to the most stable possibility. So you can see resonance stabilization makes that most stable, and that's why it's lingering a little teeny bit longer than the others. Well, let's keep going through and see what these peaks are. So over here, if you take your 99 peak, you can see that there is a CO, which is carbon monoxide, and carbon monoxide is a gas that you find in nature. So it must have some stability out there. So that's another reason why you can extrude carbon dioxide from a molecule. So here, let's take our 99 over here, and then we can see why that would kind of break up in a mass spec. So here is your carbonyl, obviously, where 2, 4, 6, 8, it's got an octet, it's fine, but still oxygen's got a charge and it wants to be neutral. So if you take that out, carbon dioxide is going to go through the chute, and you will get this cation, and you might think it's a primary and it's so bad, and how are we doing this in mass spec when we couldn't do this in SN1? Well, this is like a microsecond or less, and there are also rearrangements that are possible that stabilize that, and this is just like an incipient cation. And so that is going to give you a mass of 71 and 28 from 99. So you can see how we account for every single thing in this molecule except for that one electron. All the other masses we account for in the molecule, all the protons, all the carbons, oxygens, and so on. Okay, so we have now 71, explained. How about the others? Let's take a look. What are the other possibilities? Well, if you could do a gamma hydrogen on this side, you could also do one on this side, as you can see. All right, let's look at 60. Well, don't have things that are 11 typically, but we can think of something like this. 28 from here to here could be like an ethylene. How would you form an ethylene? Well, let's look at the possibilities. So if I have an 88, can I take out an ethylene? Well, let's look at it. So here's your 88. And let's draw this out again. So here is your radical cation. And here is your alkene. And here is your oxygen. And you can think of this kind of like your gamma here, a gamma on this side. And you can have a hydrogen out there that's just within reach. You can make 1, 2, 3, 4, 5, 6, like a 6-membered ring there. And that's great for the molecule. And so that's a possibility here. So let's look at that. Well, hold hands first. Radical, radical come together. And you can see how this can then make a radical here. And, well, this can then have your 28 CH2 getting out of there. That's 24 plus 4, 28. And you would be left with a 60 here, since we've kind of accounted for all of the atoms. So this can go over here, and you can think of something like this, where you have an oxygen. Now that you've formed a bond there, you have 2 hydrogens and a lone pair here, which is just like your hydronium ion, so there is a positive. Now they have suggested that you can have this drop over here and have a diol kind of molecule as well. That's a possibility too. All right, guys, let's look at how we can form a 43. This is a possibility. As you can see, this molecule's got a ton of possibilities, and we haven't even seen the last of it. So let's look at this is going to be the last one. As you can see, I don't have any small space, which is a good thing. So here is a rearrangement that's possible for this molecule. If you have an ionization happen on this oxygen instead of that, which is also, why not, right? All right, let's see what the possibilities are for this molecule. We can have a hydrogen that comes off here. So let's say I have a hydrogen coming off here and making a bond with that oxygen. And let's see, we want to kick this guy out. We can do it I'm just going to do it in this step. You can also make a bond and then, sever it. But then let's do this. And so you are going to get your double bonded oxygen over here. You got a lone pair and an unpaired electron. 1, 2, 3, 4, 5. So that's a plus 1. Just have 1 hydrogen here. And this is your CH3 that we've been carrying along all along on that ethyl end. But what can this do? This can also then go over here and make a bond with that oxygen and take off an H radical. So that's going to give you CH3C triple bond oxygen. Now you only have 1 lone pair here. 1, 2, 3, 4, 5. 6 minus 5 is a plus 1. And you would have your hydrogen radical take off. That is going to be, believe it or not, 28 plus 15 here is going to give you that 43. So that's 43 for you. And you can see how this long chain radical can then be taken out by the machine, you know, inside the vacuum. So just a summary, we had all of these peaks coming out of your mass spec here for this molecule. And as we said before, alpha cleavage next to the carbonyl is a very big part of the pattern for cleavage. So alpha cleavage on this side gives you the 99 peak, which is quite prominent. Alpha cleavage on this side gives you the 73 peak. Okay, it's still, you know, something that we cannot really ignore. We can also see that you can have gamma cleavage because you have a long tail. So when you have a gamma cleavage, you get this very resonance stabilized cation. That's going to be your 88 base peak. Base peak typically has some extra stability. And you can see how the resonance here would play out in this molecule. We also have smaller fragments. Well, if you're going over here, we can take carbon dioxide, and that would give us a 71. And so earlier I had these switched, this 43 and 45. So, you know, forgive me for that. I've corrected it now. We also actually, if you do 45, we really cannot ignore this 42 just because it's a little taller than the 46. And if you look at it, 60 take away 18 is going to be your 42. And 18, you know, is always water. And so if you look at your 60 here, water is all primed to leave. So you can kick this out and you can get a bond of ketene here, and that is going to have 1, 2, 3, 4, 5, a positive charge, and that's going to give you a M over Z of 42, which is going to strike the machine and give you a peak here. How would you get 29? We know 29 is an ethyl cation, and here's your ethyl tail here on the oxygen side. So you can see how this can do a gamma abstraction to give you an ethyl cation. This is then all primed up to leave as a Couch cation at 45. And I hope by now you guys are experts at mass spec. And you know all of the trends, the alpha cleavage. Sometimes when you have carbonyls and ketones, you can have beta cleavage, which is between alpha and beta. You can have gamma cleavage with that hydrogen. So a lot of possibilities here. Well, we will talk to you soon. Bye.